So picking up where we left off, let's see here. There's Jack. That's my son. Notes. Here we are. Okay, so like I said, I have practice solutions. So I'm going to close that for now because that's not what we want. Chapter 6, this is what we do want. So we've been talking about section 6.2, and get back to where we had talked most recently. We took a look at the first nice theorem for the section, differentiation of the natural logarithm. All that we had talked about last time, for the most part, was just a little bit about the natural log function and how we defined it. Okay, the way that we defined it makes differentiation really, really easy because we can make use of the second fundamental theorem of calculus. And that immediately just gives us the definition here of this first case, right? Natural log of x is defined by an integral. When we differentiate a definite integral, all right, with a variable as an integration bound, we get the original function with that variable in place. So we get very nicely exactly what we would want to get here. Natural derivative of the natural log is 1 over x. Now, if you include the chain rule at that point, right, d over dx of the natural log of u is just going to require the chain rule. So we take the derivative of the natural log, which is 1 over the input, 1 over u, and then we multiply by the derivative, d over dx of the input, the derivative of u. So this is 1 over u times the derivative of u is du dx. You could write it that way, or simply u prime, but notationally this works out to just be u prime divided by u. So however you want to think about it, maybe there were different ways that it was presented to you in the past of how to write derivatives. So the notation might need a little bit of adaptation, but overall, I think that's a pretty straightforward idea. Now, the only thing that's left that's interesting to try and take care of from this example is the derivative, or of this theorem, is the derivative of the natural log of the absolute value. Right, because this requires that x is greater than 0. This requires that u is greater than 0, but we don't always know that. Of course, we can't take the natural log of 0, so that's no good, but we could take a look at the absolute value of u to make it always positive, at least. All right, so if we do that, what we want to recognize, maybe before we get too far, the derivative of the natural log function is what? Recognize that the derivative, that the natural log of the absolute value is actually a piecewise defined function. So the natural log of absolute value of u is the natural log of u for u greater than 0, and it's the natural log of the negative of u for u less than 0. Right, we have a definition for the absolute value function. Right, in general, maybe you're not familiar with this, so I'll write it down in a moment. The absolute value is a function, and it's defined piecewise. It's defined as x whenever x is greater than or equal to 0, and it's defined as negative x for x less than 0. So the absolute value function has a piecewise definition. And then it's just a piecewise defined polynomial, right? Polynomial on its pieces. So then we have natural log of absolute value is also a piecewise function. So then when we take the derivative, we can just take the derivative of the pieces. So we say, all right, the derivative of the natural log of u is just 1, or rather is u prime. Well, let's cite the chain rule here. This is 1 over u times u prime by the chain rule. And then in this case, the chain rule says that it's 1 over u, negative u, because that's what's being plugged in. And then we multiply by the derivative of negative u, which is negative u prime. Right, a multiple of a negative just carries along. So we multiply by negative u prime. for u greater than 0. So if we simplify that a little bit, I don't have a lot of room left here, so we just need a couple more. 1 over u times u prime is u prime divided by u for u greater than 0. Oh, sorry, the second one should be less than 0 here. And then negative u prime divided by negative u for u less than 0. Of course, we have negatives in the numerator and denominator, right? A common factor of -1, so they cancel. But that leaves us with u prime divided by u and u prime divided by u. So it's the same no matter what part that you're looking at. So once you recognize that, then you can say that the derivative of the natural log of the absolute value is always going to be u prime divided by u. And of course, we don't have u equal to 0 due to the definition of natural log, right? It's not defined at 0. All right, so that's why we can ignore the absolute values when we're taking the derivative. Okay, we'll take a look a little bit later in this section about working this theorem the other direction. So if we integrate a derivative, we get back what we started with. So then that gives us the integral of these various forms. Which is something that we may have already deduced, right? Since that's how we're defining the natural log function anyway. All right. Focusing on the derivative for a moment, we want to take the derivative of these various forms involving the natural log. And it might actually be sufficient for us to consider essentially 1 or 2 examples. And we'll consider 3 or 4 examples, so that way we can also take a look at some of the other differentiation rules as well, trying to recall them. All right, so if I want to find the derivative of f in this case, f prime of x is the derivative. Our differentiation rule for the natural log says that it's 1 divided by whatever is in here, 2x plus 3, times the derivative of whatever is in there. The derivative of 2x plus 3 is just 2. So this gives us 2 divided by 2x plus 3. Simple as that. It's always the derivative divided by the original function. So I could have written the derivative in the numerator immediately, and that would have been fine. Again, the easiest way is to think of it as simply the chain rule. All right, so let's find the derivative of g of x, g prime of x. Well, before we can make it too far here, what we want to recognize is that there's a product. We have x squared times the natural log of x to the 4th plus 2. So recognizing that we have a product, we first have to use the product rule. It happens to be that the natural log is one of those functions. So the product rule says take the derivative of one of them, multiply by the other, and then take the derivative of the other and multiply by the original one. So that maybe is confusing in terms of words, but what I'm trying to say here is we take the derivative of the first, 2x, multiply by the second, natural log of x to the 4th plus 2. And then we add. Now we take the derivative of the natural log of this, or take the derivative of this, which is, let's see here, 1 over x to the 4th plus 2 times the derivative of x to the 4th plus 2, which would be 4x cubed. And then multiply by the other function, which was just x squared. All right, so once I have that, I just need to do a little bit of simplification. So I've got 2x times the natural log of x to the 4th plus 2. And then over here, so I'm going to move this down a little bit just to get a little extra room. I have a quotient, and the numerator is 4x cubed times x squared, or simply 4x to the 5th, divided by x to the 4th plus 2. Excellent. So that's it, right? We took the derivative. This is g prime of x. All right. We'll continue on. In this next case, right, there's not a whole lot that's different. We're just now saying, right, in the previous example, here we had a polynomial that didn't have absolute values around it. Conveniently, x to the fourth plus 2 is always positive. So there was no concern and no need for absolute values. When we get to this function, right, or this polynomial, that could be positive or it could be negative. Of course, the natural log is not going to be defined where this is 0, but we want to at least be able to handle where it's positive or negative. And we can do that by taking the absolute value. So now we can consider anywhere that this polynomial is non-zero. So if I want to take the derivative of h, that is find h prime of x, all that I need to do is here I can ignore the fact that we're using the absolute value. It's still just in the 1 divided by what's inside of that. So that's x cubed plus x, same thing, x cubed plus x squared minus 1. And then I multiply by the derivative, 3x squared plus 2x. All right. A little bit of simplification is not a bad idea. Again, depending on how exactly you're thinking of this, I am always thinking of it as the chain rule. So 1 divided by the function and then multiply by the derivative of the input. So derivative of the input. So if you are looking at it as following the explicit theorem that we looked at a couple pages ago, then you would have already written this in the numerator. But we can do that here. So 3x squared plus 2x divided by x cubed plus x squared minus 1. So here you might ask yourself, can I simplify this? And I don't recall if it simplifies. I know that numerator can be factored a little bit. I can pull out that common factor of x, but then there's not really anything else I can do. And I think that it's pretty clear that there's no factors that would cancel in the numerator and denominator. So this should not simplify, but I would leave it to you to attempt to factor the numerator and factor the denominator in an attempt to simplify this. All right. So now we have, let's see here, the k of x is the natural log of this cube root of a product of polynomials. All right, so if I think about this really hard, don't write this down. Watch, but don't write this down. If I wanted to find the derivative of k of x, all right, it's the natural log of this thing. Probably needed some absolute values in there. That's probably a good idea. Anyway, that doesn't matter. What I want to focus on is that the basic idea is it's 1 divided by the same thing, cube root of 3x minus 2 times x squared plus 5. But once I have that, then I have to multiply by the derivative of the input derivative d over dx of the cube root of 3x minus 2 times x squared plus 5. Right? And that in itself requires a chain rule. And you're like, oh my word. So I've got to do the power rule because it's the cube root of something. And then I have to multiply by the derivative of what I'm taking the cube root of, which is a product. So I have to use the product rule. And you're like, man, I'm just getting tired. That's so many things to do. There's so much going on. Well, logarithmic differentiation makes things a lot easier for us. And I say logarithmic differentiation because we'll use that in the next example. But here, more specifically, what I mean is that we can use the properties of logarithms to rewrite this function and make the derivative much easier to handle. So first thing to recognize is that this is the natural log of, let's see here, put it into brackets. 3x minus 2 times x squared plus 5 being raised to the 1/3 power. So we go ahead and use the power rule to say that this should be 1/3 times the natural log of 3x minus 2 times x squared plus 5. And then we use the property that a product inside the logarithm is addition outside of the logarithm. So we have 1/3 times the natural log of 3x minus 2 plus the natural log of x squared plus 5. Of course, this polynomial inside I cannot do anything with because it's combined using subtraction. And then I can't do anything here because the x squared is combined with addition, combined by addition with the 5. So there's no splitting that can occur there. But now what I have are pieces that look very, very easy. So when I go to find k prime of x, I can recognize that this is simply 1/3 because constant multiples carry along 1/3 times the derivative of this logarithmic function, which is 3 divided by 3x minus 2, right? Derivative in the numerator, original function in the denominator, plus 2x divided by x squared plus 5. So that's it. I didn't have to use the chain rule a whole bunch of times. I had to use it right here and right here, but I didn't have to use it for the power. And I didn't have to use the product rule because I could split everything up with the natural log properties. So our division, or sorry, our differentiation was much easier to handle. All right. So then what we want to do is we want to say, all right, is logarithmic differentiation or derivatives of logarithms helpful anywhere else? Yes, and it's helpful in this method that we call logarithmic differentiation. So this is a method that we're learning. So if I wanted to find the derivative of this function, find dy dx, it would require that I use, much like the previous problem, use the power rule to handle the square root. But then on the inside, I actually have a quotient. So I would have to use the quotient rule. So derivative of the square root function, keep the inside, multiply by the derivative of this quotient, which requires the quotient rule. So it would be a little bit involved. It wouldn't be horrible, but it would be a little bit involved. So what we do is we actually help simplify things by taking the natural log of both sides. So we get that the natural log of y is equal to the natural log of, now I'm going to do a little bit of rewriting right at the beginning here. This is x squared minus 1 divided by x squared plus 1 raised to the second power, 1/2 power, sorry. There we go. Making that simple change allows me to recognize that I can use the power rule for logarithms to bring that power down in front, and then use the quotient or the properties, right? The properties of logarithms to split up this as well. So this gives me that the natural log of y is equal to 1/2 times, actually, let's just write it like this, natural log of x squared minus 1 divided by x squared plus 1. Maybe a detail that's important before we get too much further. This x being greater than 1 is what allows us to know that x squared minus 1 is positive. Denominator here is always positive. Numerator is only positive for x greater than 1 or x less than -1. So we just want that so that way we have a positive number. Why do we need a positive number? Because we're taking the square root of it, and we want real number inputs and outputs. So I need the inside of the square root to be positive. That's why I want x greater than 1 here. All right. Furthermore, I don't want it to be equal to 0, and that allows me to take the natural log of it. All right. So what we're doing here is appropriate, is what I'm trying to say. So natural log. Okay, so we continue to split it up. This is the natural log of y is equal to 1/2 times, just like the last problem, natural log of x squared minus 1. Subtraction here because it's a quotient, natural log of x squared plus 1. Excellent. So all we've done is use the properties of logarithms to split up the natural log. Now what we do is we actually have to use implicit differentiation. Why? Because the left-hand side has a function of y, and y is a function of x. So I no longer have just y on the left-hand side. So when I take the derivative over here, I have a composition. The derivative of the natural log of y is 1 over y times y prime. And then on the right-hand side, I have things that look good. There's just x's over there. 1/2 times derivative of the natural log of x squared minus 1 is going to be 2x, right? Derivative of x squared minus 1 divided by x squared minus 1. Over here, derivative of x squared plus 1 is 2x divided by x squared plus 1. So now I have, I've successfully taken the derivative. Now what I want to do is I want to recognize that what I want here is dy dx, which is this thing, right? And the problem, it asks for dy dx. So maybe we want to use that notation. That would be fine. Y prime is the same notation as dy dx, or it's different notation for the same thing, rather. So if you put y prime there, that would be fine. All right, but all I want is dy dx. All I want is y prime. So I multiply both sides by y to find that dy dx is equal to y divided by 2 times 2x divided by x squared minus 1 minus 2x divided by x squared plus 1. Is that perfect? Is that absolutely everything? Are we good to go? You want to be really cautious. Read the instructions carefully. I don't think that it says here that dy dx has to be in terms of x. However, it is absolutely possible for us to do that. Right? We have y equals this in terms of x, so we can replace y with exactly that. So that would be a good idea. So this might be an okay answer. WebAssign, I'm not sure. It probably is going to have instructions for you. But when it's a case like this one where it's very easy for us to write it in terms of x, we should do that. So I have, let's see here, 1/2 times the square root of, let's see, I believe this is x squared minus 1 in the numerator. Yep. X squared minus 1 divided by x squared plus 1. And then I'm still multiplying by 2x divided by x squared minus 1 and minus 2x divided by x squared plus 1. And that's it. So now I've taken this differentiation that would have required, again, the chain rule followed by the quotient rule and reduced it to just multiple applications of what is the derivative of the logarithm. Yeah, so there was a question about x being greater than 1. So x being greater than 1 is what we're using we're saying that's the domain of the function or the domain of the relation. And we want that because values of x between -1 and +1 would result in a negative numerator or equal to 0, right? 0 or negative. We can't take the square root of a negative number. Notice the denominator is always positive. So a negative numerator would give us a negative value. A square root of a negative number would require the use of complex numbers. but we're interested in only having real inputs and real outputs. So we don't want to take the square root of a negative number. So we need x to be greater than 1 or less than -0. Yeah, so there's, yeah, this is just a clarification. There's nothing that you have to do with it. This is a necessary component. If we had that x was less than, let's see here, we had that x was less than -1, would that cause any issues in our work? I don't think that it would, because it's still, when we square it, it becomes positive, and we're far enough away that it would never be 0. So, yeah, technically this could be even not given in the problem, because you would just work with then the natural domain of the function, which would be values. Well, no, we do have to have this, because x equals 1 and x equals -1 is part of the natural domain. A natural domain is just the domain that a function takes on when it's not specified. Usually when you first talk about domains of functions and they ask you to find the domain of the function, what you're finding is the natural domain. I could certainly define the domain of this function to be all values greater than 1,000, in which case that's what I've designated. The natural domain would include 1 and -1, which would give us 0, which would mean we can't use logarithmic differentiation. So this is here to tell us we can do this. All right. Okay, so that's it for differentiation. That's it for differentiation of logarithmic functions. Now, logarithmic functions, we want to move on to that with regards to integration. So there's a bit to talk about for integration. So this is why I think we'll finish up the section tomorrow. But I'm going to stop sharing for just a moment.